Hi everyone, this is Masood Ibn Abdul Wahid. Today we are meeting together to discuss about the solution of a typical network in electric circuits. So as I said, the typical network is going to be a pyramid type electric circuit. So we are going to find the equivalent resistance of a pyramid network. The question given is this one. You could have faced this question competitive exams. In the circuit shown below, value of all the resistance is given to be 1 ohm. So you have to calculate the value of equivalent resistance between the points A and B. Now we are going to discuss the ways to find the answer. So this is the bottom layer and this is the middle layer and this is the top layer. We are going to find the equivalent resistance of the 3-layer pyramid type resistive network. To find the equivalent resistance, let us give some numberings. So let us see the network in a different perspective so that we can have a better understanding about the mode of connection between each resistance. So to do so, let me redraw the given network in a different perspective like this. So let us call this two nodes to be A and B. 1, 2, 3, 4 are rearranged to be in a vertical way like this. 5, 6, 7, 8 are rearranged to be in this manner. So now let us connect the resistances as given in the network. Between the points A and 1, we have resistance R1. So between A and point 1, the resistance R1 is connected. Between points A and 2, the resistance R2 is connected. In the similar manner, we will connect R3 and R4 also like this. Between the points 1 and 2, the resistance R5 is connected. Here also, we will connect between 1 and 2. And in the similar fashion, between 2 and 3, we have R6. Between 3 and 4, we have R7. And between 4 and 1, we have R8. Between 1 and 5, we have resistance R9. Between 2 and 6, we have R10. And between 3 and 7, we have R11. Between the points 4 and 8, we have R12. So between 5 and 6, we have resistance R13. And between 6 and 7, we have resistance R14. Between the points 5 and 8, we have resistance R16. Okay, between 5 and point B, we have resistance R17. And between the points 6 and B, we have the resistance R18. And between the points 7 and B, we have resistance R19. And between points 8 and B, we have resistance R20. So just we have recreated the given network in a different fashion so that we can see it in a different perspective. We can analyze it easily. We can understand it easily. So let us take this recreated diagram into a new slide. The same network is taken once again in a bigger scale in a new slide. Now, let us assume that a current I is passing into the network through the point A. So after point A, as all the resistances are of equal value, this current I after the point A will divide into 4 equal parts. So namely, so the current through R1 will be I by 4, the current through R2 will be I by 4, the current through R3 will be I by 4 and also the current through R4 will be I by 4. So this is so because we have the resistances R1, R2, R3 and R4 to be equal. Now as you can see, the resistance values and the current values both are equal. So we will end up with a equal voltage. So the voltages in the points 1, 2, 3 and 4. All the 4 voltages will be equal. Similarly, the voltages at points 5, 6, 7, 8, namely V5, V6, V7, V8, all these 4 voltages will be equal. As the voltages are equal, you can simply short circuit those points because there is no voltage difference. There is no potential difference between the point 1 and 2, point 2 and 3, point 3 and 4. Also, there is no potential difference or voltage difference between point 5 and 6, 6 and 7, 7 and 8. So before this, we have some resistors called as R5, R6, R7, R8. So now, during the simplification, we have found that these potentials are equal and there will be no potential difference. So there will be no currents through these resistances R5, R6, R7, R8. Also, there will be no current through the resistors R13, R14, R15 and R16. So we can simply short circuit these resistances like this. With a simple circuit where we have 4 resistances connected in parallel. And like this, we have 3 group of resistances. Okay. So in this network, the point A and B is located here. And the points 1, 2, 3, 4 are merged together as it is having equal potentials. Similarly, the points 5, 6, 7, 8 are merged together as it is at equal potential. There is no potential difference between the points, so it is merged together. So now the simple network, what you can see here is, as I said, 4 resistances are connected in parallel, like that 3 combinations or 3 groups of resistances we have. So now we can group these 4 resistance to be R equivalent 1, and we can group these 4 resistances to be R equivalent 2, and we can group these 4 resistances to be R equivalent 3. You can see that all the resistances are of equal values, so we will end up with a condition that R equivalent 1 will be equal to R equivalent 2 will be equal to R equivalent 3. Now let us find one of those resistance. R equivalent 1 we will find. So as it is connected in parallel, the equivalent resistance will be given by the equation 1 by R equivalent will be equal to 1 by 1 plus 1 by 1 plus 1 by 1 plus 1 by 1, which implies 1 by R equivalent is equal to 4. In turns, R equivalent 1 you can find it to be 0.25 ohms. R equivalent 1, R equivalent 2, R equivalent 3. All the 3 values will be equal. We will connect these 3 resistances as required. Because all the 3 parallel groups are connected in series, the total resistance between the required points A and B, RAB, will be equal to 0.75 ohm. So this is how we can able to simply reconstruct the diagram or review the diagram in a different perspective, so that it will ease our solution like what we have discussed so far. So like this, you can solve a pyramid type network, a cubical network, or such a similar kind of networks. You can easily solve by just having a different perspective of the diagram, of the given network diagram. To assist you, let us see the same solution in a software to ensure that whether the potentials of 0.1, 2, 3, 4 and 0.5, 6, 7, 8 are equal, and whether we are getting the same result in the simulation. Just to create an awareness about the software, I'm drawing the same diagram in the simulation, and let us see what the voltages are and what the final value of resistance we are getting in the simulated diagram. As I said, the same given pyramid network was drawn in the simulation software. It is called Proteus. So here you can see the blue color items. All these are going to display the node voltages or the point voltages. So this is the point 1, 2, 3, 4, and these are the points or nodes 5, 6, 7, 8. So all the blue color items are going to display the node voltages or the point voltages once we connect with a battery. Of course, the given circuit is not having any battery. Just to display you or just to demonstrate to you what is the voltages and how it is equal, I have connected a battery. So now I am playing the simulation, running the simulation. So let me zoom it for better visibility. You can see here. So this is the node 1, which is having a voltage of 2, node 2 a voltage of 2, node 3 the voltage is 2, and the node 4 is of voltage 2. So now let us see the voltage of the nodes 5, 6, 7, 8. You can see here the node 5 or the point 5 is having a voltage of -2, and the voltage of node 6 or 0.6 is also to be in -2 volt, and the voltage of node 7 or 0.7 is also of -2 volts, and here comes the last node, which is the node 8. Again it is of -2 volt. As we discussed previously, so all these 4 nodes are having equal resistance values and equal current values, so the voltages of these 4 nodes will be equal. Similarly, the voltage of the outer 4 points will also be equal, and that is what I try to illustrate in this simulation. Also, we will connect a ohm meter across the points A and B, and let us check what is the resistance we are getting through the simulation. And the ohm meter is connected between the points A and the point B. Now if we run the simulation, it will display the equivalent resistance or the value of resistance between the points A and B. So which you can see it to be, I will zoom it, so which is to be 0.75 ohm. Of course, the purpose of this Proteus is to create an interest to you, or to just, if you are not aware of this Proteus software, just to introduce you, there is such software where we can connect the electrical electronic circuitries and we can analyze the current through some elements or the voltage across the element. Any performance of a network can be analyzed, maybe an electrical or an electronic network. We can connect here and we can simulate here and we can analyze about the currents, voltages, parameters, whatever we are in need of. So the same value of equivalent resistance between the points R, A and B calculated manually, and also just now we discussed how to simulate in the Proteus. So now as a conclusion, so during the discussion in the today's video, we have analyzed some basics about the pyramid network, and we have discussed about how to get the equivalent resistance of the given pyramid network. The same circuit was simulated in Proteus to analyze about the node voltages, point voltages, and to verify the equivalent resistance what we got is coming in the simulation or not, and to find the correlation between the manual calculation and the simulated answers. I hope this video was a useful one to you. So if you have any queries, or if you have any comments, or if you want to solve any such similar networks, you can say it in the comments. Thanks for watching. We will meet in the next video. Until then, it is Masood Ibn Abdul Wahid signing off.